Welcome back to AI Unraveled, your daily briefing on the real-world business impact of AI. The convergence of two massive existential threats is redefining enterprise security: AI vulnerabilities and the impending quantum era. We're no longer just dealing with simple data breaches. Today, your AI models face insidious data poisoning, evasion attacks, and model inversion, exploiting the very nature of machine learning. Simultaneously, the ticking clock of quantum computing allows adversaries to use the harvest now, decrypt later strategy, threatening to render every piece of classical encryption obsolete. This is not a future problem. It is a current vulnerability. But first, a word on reaching the right audience. Are you still marketing to the general public? Stop. Your platform solves the hardest challenge in tech, getting secure, compliant AI into production at scale. But are you reaching the right 1%? AI Unraveled is the single destination for senior enterprise leaders, CTOs, VPs of engineering, and MLOps heads who need production-ready solutions like yours. We have reserved a limited number of high-impact mid-roll ad spots. This is a direct line to your most valuable buyers. Don't wait for the competition. Secure your spot immediately at the link in the show notes or email us. This week, we introduced the definitive defense, the Zero Trust AI framework for a quantum-resilient enterprise. We break down the three mandatory pillars of this strategy: implementing Zero Trust MLOps to secure the entire AI lifecycle, establishing verifiable provenance using tamper-proof tech like blockchain for model integrity, and mandatory adoption of post-quantum cryptography, PQC, to future-proof your entire data foundation. You cannot afford to wait. Tune in to understand how to build a shield that protects your competitive edge against tomorrow's threats. That's all coming up right after the break.
Welcome to the deep dive. So, if you are running an organization today, chances are artificial intelligence isn't just some cool side project anymore, is it?
No, not at all. It's really becoming a critical enterprise asset.
Exactly. It's driving, drug discovery, financial modeling, logistics, core functions.
Right. But the thing is, that critical asset faces a new and frankly profound security crisis.
We're calling it the converging storm.
That's a good way to put it.
Yeah, it feels like a storm. It's dual-pronged and, well, existential, really. On one side, you've got these unique intrinsic vulnerabilities, things that exploit the core statistical logic of machine learning models themselves.
Not your typical software bugs.
No, exactly. And then on the other side, there's the quantum decryption threat. It's like rapidly making classical cryptography, well, obsolete.
And this is really where traditional security models just completely fall apart.
Right.
If you've been relying on that old, castle and moat perimeter security.
The trust but verify idea.
Yeah, where internal network stuff is kind of implicitly trusted. That is just a catastrophic liability now, especially in the age of AI.
Because AI is so distributed.
Exactly. AI models are distributed. Their data pipelines can be really opaque. And maybe most importantly, the fundamental encryption layer protecting them basically has an expiration date.
Okay. So if legacy security is, as you say, fundamentally broken, what's the alternative? What architecture do we actually need to build for the future?
That's the key question.
So our mission today, for you listening, is to give a complete picture of this whole threat landscape and then lay out the strategic solution, what we're calling the quantum resilient zero trust AI framework. It's built on three foundational pillars.
Sounds good. Let's get into it.
Okay, let's unpack that first prong of the storm then. The intrinsic weaknesses of the AI itself. And like you said, we aren't talking about generic code bugs here like SQL injections or buffer overflows.
No, these are different. These are exploitable features tied directly to how machine learning works, how it relies on statistical training data.
So where do we start? Maybe at the beginning of the process.
Let's start right at the beginning, yeah. The MLOps lifecycle. Think about data poisoning.
Okay.
This is really insidious because it targets the model during the training phase. The idea is an adversary injects malicious or maybe mislabeled or just corrupted data.
Right, but how easy is that for someone on the outside? Does this pretty much need an insider or maybe a compromised data supply chain? Or can, like, a regular hacker actually inject bad data?
Well, it definitely requires access to that training pipeline. So yeah, insider threats and supply chain compromise, those are critical vectors here.
Okay.
The goal is corruption right at the foundational level. And the research shows the impact isn't subtle. We're talking about potentially causing an autonomous vehicle model to mistake a stop sign for, say, a yield sign.
Wow.
Or You probably remember the Microsoft Tay chatbot incident.
Oh yeah, that one's sideways fast.
Exactly.
Yeah.
User inputs very quickly poison the model, basically forcing it to generate really offensive content. That's data poisoning in action, albeit a more public version.
Okay, so that's corrupting the training. What happens once the model is actually trained and, deployed out there? That's when attackers try to steal the knowledge, right? Things like model inversion and inference attacks.
Correct. Yeah. These attacks work by exploiting a trained model's outputs, trying to reverse engineer sensitive information about the private training data it learned from.
How does that work?
Well, if an adversary can query your model repeatedly, they might be able to perform membership inference, basically figuring out if your specific data was used in training.
Oh,
Or even attribute inference, deducing sensitive characteristics like maybe medical conditions or financial status from the model's responses.
that sounds like a direct route to, well, catastrophic privacy violations.
Absolutely.
Oh.
If you're dealing with PII, personally identifiable information, or PHI, protected health information, this opens organizations up to massive regulatory penalties. Think GDPR fines.
Right.
And it's particularly dangerous if the model was what we call overfit, if it essentially memorized chunks of its training data.
Which can happen easily if you're not careful during training.
For sure.
Okay, so we can attack the data going in that's poisoning. We can steal secrets coming out, inference attacks. What about attacking the model when it's like actively making decisions in real time? That brings us to evasion attacks, doesn't it? Or what people call adversarial examples.
Exactly. These are attacks that happen right in the moment of inference, when the model is being used.
How do they work?
The attacker makes extremely subtle changes to the input, often things humans wouldn't even notice, maybe changing just a few pixels in an image or adding some carefully crafted noise.
So to us, the input looks normal.
Yeah, basically the same. But to the model, these tiny changes are enough to force a specific incorrect prediction. This is kind of a favorite method for trying to compromise safety-critical systems. There's that well-known example of using strategically placed stickers on a stop sign
Right, I've seen that.
to trick a self-driving car's AI into misclassifying it. It fundamentally weaponizes the model's blind spots.
And now that large language models, LLMs, are pretty much everywhere, there are new threats specific to them too, right? First one that comes to mind is prompt injection.
Oh, definitely.
Yeah.
That's a big one. It's essentially embedding malicious instructions right inside a user's prompt.
What's the goal there?
The aim is usually to bypass the LLM's built-in safety features, its guardrails. Trick the model into revealing maybe internal configuration data, or executing actions it shouldn't, or simply generating harmful or biased output.
Okay. And the second LLM-specific threat, hallucination abuse. This one feels deeply unsettling to me. It exploits that core tendency of LLMs to sometimes just, well, make stuff up that sounds plausible.
Exactly. It exploits the hallucination tendency. Attackers can actually seed the public web with synthetic, fake content, phony websites, fake articles, that kind of thing.
And then the LLM finds this fake stuff during its training or when searching.
Precisely. The LLM relies on that web data. So this attacker-created fake content can end up legitimizing misinformation, which the LLM then amplifies because its poisoned sources make the hallucinations sound convincing, even true.
Wow. Unsettling is the right word.
But here's the crucial pivot point.
Yeah.
What's really fascinating and worrying is that even if we somehow developed perfect defenses against every single AI-specific attack vector we just talked about, the fundamental layer of protection underneath it, all our classical cryptography, is simultaneously under an existential threat from quantum computing.
Okay, so this brings us squarely to the second part of the storm, the quantum decryption threat, and the famous, or maybe infamous, Q-Day. Can you just clarify for us why the math that has basically secured the internet for decades is suddenly doomed?
Yeah, it really comes down to the work of mathematician Peter Shor back in 1994.
Yeah.
Shor's algorithm. When you run that algorithm on a sufficiently powerful quantum computer, what we call a cryptographically relevant quantum computer, or CRQC, it can efficiently solve the two hard math problems that underpin virtually all modern asymmetric encryption.
So that's algorithms like RSA, ECC, Diffie-Hellman.
Exactly. The ones securing your VPN connections, your secure websites, HTTPS, your email encryption, your digital signatures, financial transactions. The list goes on.
And the consensus timeline for a CRQC, the kind of machine that can actually run Shor's algorithm effectively and break these codes, it's looking like within the next decade, right? Maybe around 2030 to 2035.
That's the general time frame most experts are converging on, yes. Which leads us to the most critical immediate danger today. The concept of harvest now, decrypt later, HNDL.
Okay, explain HDL, because you said immediate danger, this isn't a future problem.
No, this is absolutely happening right now. Sophisticated adversaries, think nation states or very well-resourced groups, are already actively exfiltrating and storing massive volumes of currently encrypted data.
They're just hoarding it.
Exactly. They're hoarding it now, betting on the future arrival of a CRQC to unlock that stored trove later. They don't need to break the keys today. They just need to collect the encrypted data and wait.
So this basically puts an expiration date on any long lifecycle data that's only protected by classical encryption today.
Precisely. Think about it. If you have proprietary training data, maybe sensitive R&D for a new drug, or industrial secrets that needs to remain confidential for, say, the next 20 years, well, 2035 falls well within that 20-year window. So the classical encryption protecting that data today is already insufficient against a future quantum adversary.
That's a sobering thought. What kind of AI assets are prime targets for this HNDL strategy?
It's the crown jewels, really. The raw proprietary training data itself, which might contain PII or PHI, the distilled intellectual property contained in the trained model weights and parameters, and of course critical corporate trade secrets that might be transmitted or stored encrypted.
Wow, okay. And if that wasn't enough bad news, the relationship isn't just one way, is it? It's not just quantum attack and classical security. Quantum computing itself could potentially be weaponized against AI models. Tell us about quantum adversarial machine learning, or QAML.
Yeah, QAML is another emerging concern. The idea here is that quantum algorithms, because of their potential processing power, might be able to explore the really complex parameter spaces of neural networks much more efficiently than classical methods.
What would that allow an attacker to do?
It could potentially lead to the generation of much more subtle, maybe more potent adversarial examples, those evasion attacks we talked about earlier.
Harder to detect.
Possibly harder to detect, and maybe requiring fewer queries to the target model to find a successful attack. That would make them incredibly difficult for our current AI defenses to spot.
So our AI defenses themselves need to become, what, algorithmically agile, ready for threats we haven't even fully seen deployed yet?
That's exactly right. We need defenses ready to adapt to quantum-enhanced threats down the road.
Okay. So, summing up this part, we have these novel attacks targeting AI data and decisions. And at the same time, the very foundation of trust classical cryptography is crumbling under the looming quantum threat. It really is a perfect storm.
It is.
So, what does a future-proof defense actually look like? How do we navigate this? This is where that strategic framework comes in, right? The 3 pillars of quantum resilient zero trust AI.
Correct. We need a holistic strategy.
Let's start with pillar 1, zero trust MLOps. What does that mean in practice?
Okay, so zero trust MLOps is about securing the entire process where AI is developed, trained, and deployed. The absolute core principle has to be never trust, always verify.
So no more implicit trust just because something is inside the network perimeter?
Absolutely none. Implicit trust based on network location is eliminated. This applies across the entire machine learning operations MLOps lifecycle. Development, training, deployment, monitoring, everything.
How does that actually translate into practice? Say in a CI/CD pipeline for machine learning, what changes?
Okay, well first is continuous verification. You have to strictly authenticate and authorize every single entity, whether it's a user, a data pipeline, an inference API for every single action they try to take.
Give me an example.
So maybe your CI/CD runner script needs to pull a data set for testing. Instead of using a long-lived API key or secret that could be stolen, it uses a short-lived, dynamically generated token that's valid only for that specific task and expires quickly. Much harder to misuse.
Makes sense. What else?
Then you rigorously enforce least privilege access, granting only the absolute minimum permissions required for any task. For instance, an inference server in production. It should only get only access to the final model artifact. It shouldn't be able to read the weights directly or modify them.
Right. Preventing tampering or theft. And I guess microsegmentation fits in here too, kind of limiting the blast radius if something does go wrong.
Exactly. Logically isolating different parts of the MLOps environment, like separating your data ingestion zone from your training environment and keeping the model registry highly secured. If an attacker breaches one segment, say data ingestion,
they can't easily jump over to steal the production model?
Precisely. It contains the damage. And this all has to be built on the assume breach mindset.
Meaning you assume attackers are already inside.
Yes. So the focus shifts heavily towards detection and response. You need real-time behavioral monitoring to spot anomalies. For example, the system should absolutely flag it if a data scientist suddenly starts downloading an entire terabyte-sized data set at 3 a.m. from an IP address in a country they've never worked from.
Because that could indicate model theft or data exfiltration is happening right then.
Exactly. It's about spotting suspicious behavior, not just relying on firewalls.
Okay, so that operational rigor, that zero trust approach to the process, seems like the antidote to attacks like data poisoning or unauthorized access. Let's move to Pillar 2, verifiable provenance. This sounds like it shifts the focus from who accessed the system to guaranteeing the integrity of the assets themselves.
That's right. How do we know for sure that the training data we're using or the model we've deployed hasn't been secretly tampered with somewhere along the line, even if all the access controls were perfect?
So how do we achieve that? How do we verify the artifacts?
Well, you need an immutable chain of custody, a verifiable record. And this is where technologies like permissioned blockchain can actually be very useful, not for cryptocurrency, but purely for security logging.
How would that work?
You use the blockchain to record cryptographic hashes. Think of them as unique digital fingerprints of key artifacts at critical stages. Like you hash the data set when it's ingested, you hash the model code, you hash the final trained model artifact before deployment.
And these hashes are stored on the immutable blockchain ledger.
Correct. So later, if an auditor or even an automated system needs to verify integrity, they just recalculate the hash of, say, the model currently running in production.
Yeah.
If that hash doesn't match the one recorded on the blockchain for that version.
You have instant, undeniable proof of tampering.
Exactly. It provides verifiable integrity. Now, another really interesting tool in this pillar, though maybe more forward-looking for complex tasks, is secure multi-party computation, or SMPC.
SMPC.
Right.
That's the idea where multiple parties can work together on data without actually revealing their private data to each other.
Yeah. It allows multiple organizations, say different hospitals, to jointly compute a function, like training a really robust AI model for cancer detection using their combined private patient data, without any single hospital or even the central server doing the computation ever seeing the raw, unencrypted patient records from the others.
That sounds revolutionary, especially for sensitive data in healthcare or finance, training on confidential data without ever actually decrypting it or sharing it. But is SMPC really practical for large-scale, complex AI models today? Or is it still mostly limited to smaller, maybe proof-of-concept uses?
That's a very important practical question you're right to ask. While the cryptographic theory behind SMPC is sound, it is computationally expensive.
Meaning it's slow and needs a lot of resources.
Yes, it incurs significant latency and resource overhead compared to traditional training. So currently, it's often restricted to maybe smaller data sets or less complex models or more targeted AI applications. However, the performance is improving rapidly with new research and hardware acceleration. It remains a critical long-term strategy for achieving that absolute data confidentiality during collaborative AI training.
Okay, so SMPC is maybe more on the horizon for big models, but verifiable hashes using blockchain are doable now. That covers Pillar 2. Finally, Pillar 3. Crypto agility and quantum resistance. You mentioned earlier, the first two pillars rely on verification, often cryptographic verification. But if the cryptography itself is broken by a quantum computer, then the whole structure fails.
Yeah.
Exactly. The first two pillars are built on a foundation of verification, and if that foundation crumbles, none of the controls matter. So we absolutely have to future-proof that cryptographic foundation.
And this brings us back to post-quantum cryptography, PQC.
Yes. This is the mandate for PQC. The transition is not optional, and it's already underway, largely driven by the standardization efforts from NIST, the U.S. National Institute of Standards and Technology. They published the first set of final standards in 2024.
Right. And these new algorithms, things like MLChem for encryption and MLDSA or SLHDSA for digital signatures, they use different math problems. Correct. They rely on mathematical problems, primarily from areas like lattice-based cryptography or hash-based cryptography that are believed to be computationally hard for both classical computers and quantum computers to solve efficiently, unlike the problems Shor's algorithm breaks.
So this means basically everything needs to migrate. Data encryption in transit, data encryption at rest, the digital signing of code, model artifacts, provenance logs, everything used in that zero-trust MLOps pipeline.
Everything that relies on asymmetric cryptography today, yes, it's a huge undertaking. But why the specific emphasis in this pillar on crypto agility? Why not just say migrate to PQC?
Good question. Why agility?
Because, honestly, the PQC field is still relatively nascent compared to classical crypto. These algorithms haven't been subjected to decades of global scrutiny like RSA has. We need to architect our systems with the capability to rapidly and, ideally, seamlessly swap out cryptographic algorithms, keys, and protocols without having to completely redesign the entire system architecture.
So if a potential weakness is discovered in one of the new PQC standards, say 5 or 10 years from now,
Agility ensures you can transition quickly to a different, perhaps newer or patched algorithm and minimize your window of vulnerability. You're not locked into something that might turn out to be flawed.
that makes sense. And this transition, it even affects the physical hardware we use, doesn't it? Things like hardware security modules, HSMs that protect the most sensitive keys. We found that these PQC algorithms often have significantly larger key sizes.
They do. Much larger keys and often larger signatures compared to classical algorithms like RSA or ECC. This puts a strain on existing HSMs, both in terms of storage and processing power.
So how are HSMs adapting?
Well, new PQC-adapted HSMs are being designed specifically to cope with this. One common approach is moving towards storing smaller cryptographic seeds securely within the HSM boundary, and then deriving the larger, full private key on demand only when needed, still inside that secure physical chip.
Ah, so the master secret stays small and protected, but the working key can be generated as needed.
Exactly. It ensures that the root of trust for all the keys used throughout your zero trust framework is protected both physically inside the HSM and algorithmically against future quantum threats.
Okay, that covers the 3 pillars.
So just to summarize for you listening, securing modern enterprise AI really demands this fundamental architectural pivot. You absolutely need zero trust MLOps to secure the environment and the operational processes. You need verifiable provenance to guarantee the integrity of your critical data and models. And you need post-quantum cryptography combined with crypto agility to ensure that the foundational encryption layer remains sound now and against the future quantum threat.
And listening to this, it feels like more than just a technical project, doesn't it? It really sounds like a fundamental business strategy now for protecting what might be the most valuable IP, the crown jewels of the 21st century enterprise.
I completely agree. It has to be driven from a strategic business risk perspective.
And the urgency is there. The threat is active right now through that HNDL strategy. The NIST standards for PQC are available. We're seeing industry leaders already executing on transition roadmaps. Microsoft, for example, has a public target for full transition around 2033. The time for just talking about it, well, that seems to be over.
The time for planning and execution is definitely now.
Which leaves us with maybe this final provocative thought for you to consider as you evaluate your own situation. When you look at your most sensitive AI assets, your most valuable data today, you really can't assess the security of that data solely by the strength of its current encryption anymore.
No, we can't.
Instead, you have to evaluate that security based on its required confidentiality lifetime. How long does this data absolutely need to stay secret? Versus the projected arrival of a cryptographically relevant quantum computer, maybe around 2030, 2035.
Exactly.
So if you have sensitive data, maybe R&D, maybe customer PII, that absolutely must remain confidential for the next 20 years. Is the classical encryption protecting it today already insufficient against that future threat?
That's the critical calculation.
Yeah, that calculation is really what must drive your security roadmaps starting today.
That's it for today's deep dive. We hope you walked away with actionable insights for your enterprise strategy. Before you go, let me remind you of the unparalleled value of this platform. AI Unraveled delivers deep, uncompromised technical insight that keeps our audience, senior enterprise leaders, tuned in to the very last minute. That sustained attention is the best place for your ad. This is your opportunity for a direct line to your most valuable buyers, the CTOs, VPs of engineering, and MLOps heads who sign off on high-stakes infrastructure. Stop wasting budget on general marketing noise. Secure your high-impact premium ad campaign right here. Email us today to reserve your mid-roll package, info@djamgatech.com. Thank you for listening to AI Unraveled. We'll be back tomorrow with more.